All right, thank you very much. I would like to thank the organizers, as usual, for setting up this nice workshop. So I'm going to introduce L1-algebras in the context of double and exceptional field theory, and in fact even a little more general for general field theories. And this is based on the longer papers Barton Sliwa from last year, 2 papers with Henning, and also some work in progress. All right, let me start by making a few general sort of philosophical remarks that should give you like a little roadmap of where I'm going with this talk. So the big motivation here is duality covariant formulations of certain theories, namely first gauge supergravity theory is written in a certain formalism called the embedding tensor formalism, which turns out to be extremely efficient in order to construct these theories. And the second example being double and exceptional field theory. And both are in fact very closely related in a way that I think I will make more precise during this talk. And both require the introduction of redundant or unphysical objects. So in some sense that's a natural generalization of what we do all the time in gauge theory, where we introduce unphysical or redundant fields, namely gauge fields, in order to make certain features manifest, like Lorentz invariance or locality. And the price we have to pay is that we have to introduce these redundancies. And so in some sense, this theme here, in the context of these 2 types of theories, is a continuation of that. So there's some kind of higher notions of equivalence, where we have equivalences between equivalences, etc., etc. So it keeps going. In fact, that's a general theme that also arises in algebraic topology and homotopy theory. And this is a quote by my colleague Stonybrook, Dennis Sullivan. So in this context, these infinity algebras that I'm going to introduce are very natural because they allow us to live with slightly false algebraic identities in a new world where they become effectively true. So what that means is that certain features we always take for granted for physical theories, like for instance the statement that the continuous symmetry is sort of synonymous to the existence of Lie algebras, do not need to hold exactly. So you have to sometimes write equations that on the face of it look sort of wrong, they're not exactly satisfied. But the catch is that it's enough if they only hold, in the mathematical language, up to homotopy. And I will discuss examples of this, and I think it's fair to say that it's becoming more and more clear, it seems more and more likely, that these features provide deep pointers for the so-called elusive underlying mathematical structure of double field theory, exceptional field theory, and sort of string theory, M theory in more generality. So that's the roadmap. And now let me give you an overview. So first, I will introduce these L1-algebras, or it's also called strongly homotopy Lie algebras. And then I will discuss how they arise in general field theories. And so there's a general map between, sort of, general dictionary between field theories and L1-algebras. But one of the main motivations is to construct what's called a weakly constrained double field theory, which would be a subsector, an exact subsector, and closed subsector of the full closed string field theory, which so far could not be constructed, but we have reasons to believe that it must exist and must be governed by a suitable L1-algebra. So then I will change gears a little bit, and I will introduce algebraic structures which are called Lightness or low-day algebras, which are also generalizations of Lie algebras, and which are one class of algebras that give rise to L1-algebras. And they are very interesting because they are sufficient in order to define Chern-Simons gauge theories in 3 dimensions. So in fact, they arose already in gauge supergravity and exceptional field theory, although the mathematical structure has not been sort of quite made explicit until recently, and that's what I'm going to explain here. And that's sort of the simplest setup where you can see those infinity structures arising. And then I will discuss some more recent results, which explain the embedding tensor formalism that I mentioned from a more abstract and more general point of view, in which these Lightness algebras can be realized through a Lie subcomplex general Lie algebra, but defining the Lightness algebras in terms of a co-adjoint action of this Lie algebra. So that probably sounds mysterious at this stage, but I will explain it in a little while. And then I close with some general remarks. All right, so let me start with the L1-algebras. So here's the definition. So the L1 is a generalization of the Lie algebra, which was introduced in the physics literature by Zwiebach, and in the math literature, I'm not quite sure, but this is here standard reference, Lada-Stashev. And so this is defined on a vector space that has a graded structure, so in general it can be graded over the integers. And you equip this vector space with multilinear graded and isometric brackets. So it means you have these maps with n inputs denoted by Ln, the map, and it lives in the same vector space, and it has a definite degree. So the degree of the output is determined by the degrees of the input, and in the conventions I'm using here, these brackets also have an intrinsic degree. Never mind the details. But the important feature is that these higher brackets have to satisfy generalized Jacobi identities. So there's now an infinite series, potentially infinite series of generalized Jacobi identities that generalize the familiar Jacobi identity from Lie algebras, which are written here. So also that looks very messy. Never mind the details. The important point is that this is bilinear in these maps, I and j, and these, for each n, these degrees here have to add up to n plus 1. And then you have to do certain permutations of the arguments and include certain sign factors. The details are explained here, but I'm not going to go through it. There's a specific prescription of how to write these relations and how to compute the signs, which via the so-called costural sign take the degrees into account. But the important point is that these identities bilinear in L, and to get some intuitions we can write them out for low n. So for n equal 1, we learn that this map L1, which is not really a bracket, because it just is one input that gets you one output, so it's really a map. In this case, it just tells you that it's nilpotent, L1 squared is 0. Then for n equal 2, we get the relation that L1, which we just have here, acts on L2, which you can think of that's the part that is so generalized as the B bracket. There's two inputs and one output. And this L1 acts as a derivation on L2. So if you take L1 of L2, you can sort of move the L1 inside via the Lightness rule up to the sign. Now for n equals 3, we finally get to the generalization of the Jacobi identity. So for n equals 3, we learn that the Jacobi identity only holds up to homotopy, by which I mean here that you get these bilinear expression L2, so 3 terms, which is the standard combination that you would have before the Jacobi identity. But this by itself does not need to be 0. In fact, it can be corrected if you have an L1 and L3 of this form here. So this is sort of the failure of L1 to act as a derivation on L3, and if you have an L3 that is non-trivial, you can sort of relax the standard Jacobi identity. And then it continues forever. For n equal 4, you get this combination here. And there's an infinite set of relations, potentially. All right, so that's the abstract definition of an L1 algebra, which I'm sure you've already seen earlier during this conference. But any questions so far? Okay, so now let me explain what that has to do with field theory. So for a general field theory, the claim here is that the general field theory can be described in the language of L1 algebras as follows. So here I have this graded vector space written out. So we have an x0, x minus 1, x minus 2, and it potentially extends in all directions. And note here that this map L1 has an intrinsic degree of -1, the convention I'm using. So the claim is now that each of these spaces has a concrete interpretation in standard field theory terms. For instance, the space x0 here is the space of gauge parameters. So that's the space on which the gauge structure lives. So the psi here, living in the space, you should think of as a gauge parameter. The space x minus 1 is the space of fields, denoted by psi here. And then the space x minus 2 is also the space of field equations, which you think of it as a different space. And potentially can continue in this direction here if you have gauge symmetries or gauge symmetries. This is then the space x1, also space of trivial gauge parameters.
where is the conflict here? VV-VRST complex?
It is linear.
Did you ask a question or what's the statement? So what's the question?
Is this the VV-VRST complex?
It is certainly closely related, but not so far, not exactly. I mean, that's just sort of an independent.
I think it is precisely the VV-VRST complex. If L1 is a linearized piece, then it is if a theory is linear, so you have only L1, then this is precisely VRST complex, and the grading is Gauss number. Well, not necessarily Lagrangian systems.
Sorry, what is the grading?
Gauss number. Of course, where to put 0 in Gauss number is a matter of convention. Standard choice in VRST is to have fields in degree 0.
Yes.
It is.
So I mean, so far just discussing, so the point I'm trying to make is that you don't have to know anything about VRST and VV. You don't have to think about quantization at all. You just take it as a classical field theory, and there's this dictionary. So in that sense, I'm trying to make a point that is perhaps a little more general. So, so the structure of that we have here by any field theory is that in general we might have gauge transformations and field equations, and they can all be written in terms of these structures, in terms of these brackets. So the gauge transformation of psi, so as an object in x minus 1, is given by L1 of psi, so that's the linearized piece of the gauge transformation. And then you can have higher order pieces, so you can have L2, psi and psi and L3, and potentially can continue forever. And then you have the field equations, which are written here, which also start with the linear piece, L1 of psi. Now you see here you act the L1 of psi brings in this space x minus 2, which therefore is, we think of as a space of field equations. And so they can also have higher order terms. And now the claim is that all the standard consistency checks you would do in the field theory, so if I write down potential gauge transformations or potential field equations, you have to check that the gauge transformations are consistent, that they're close, you have to check that the field equations transform covariantly, and all these things. And the statement is that all these relations are sort of exactly implied by these L-infinity relations. So in that sense, there's an extremely natural map between the data of an L-infinity algebra and the data of the field theory. Yeah, and also I should say, so you can also encode the trivial parameters here. So if you have a psi that is an L1 of chi, so that comes from the object here via the L1, this x trivial. So that you can write for any field theory you like, but of course the most interesting cases are those where you really need that structure in a non-trivial way. And the simplest example, I guess, is the current algebrite or the gauge structure of double field theory. So David already briefly mentioned this new bracket that one has, which is the current or C bracket. That defines an L2. That, however, does not define in the Lie algebra. So here we really need the full machinery of L-infinity. We have to define a non-trivial L3 and a non-trivial L1, so that these relations that I had in the previous slide are satisfied. And that indeed defines an L-infinity algebra as shown by these people. Now the reason that's interesting is that in double field theory, eventually we want to generalize it to a weakly constrained theory. So what David explained to you is that we usually impose this constraint, which is called the strong constraint, which essentially is just a way of saying that only half of the coordinates are physical. So we have a condition like this, where the construction, the ODE covariant construction between the derivatives is 0. Now, in the full string theory, we know that momentum and winding modes are physical and exactly on the same level. So there should be a theory which really encodes both sets of modes, and that would require imposing only what's called a weak version of the constraint. So let me just write it down. So we want to work with functions that satisfy this condition, but not necessarily impose that if you take the product of some functions satisfying this condition, that this is also 0. So in general, this may be non-zero, but that's really sort of the setup that string theory suggests. And the problem here is to define now a consistent theory where this is satisfied. Yeah,
In the case of David, it was motivated by rules applying
right.
that kind of condition. Here, it's just a simplification, or is there something analogous?
Well, my motivation is just different. It's not Kaluza-Klein.
Right.
It's so that the full, so double field theory came originally out of the full closed string field theory. So we know the full string field theory, it's not really like Kaluza-Klein. Both sets of coordinates are present and physical and active. The question is, can I write this theory explicitly? And so more precisely what we want here is a truncation of the full closed string field theory to sort of a subset of massless fields, so metric V field and dilaton, for instance, the simplest setup, plus the infinite tower of Kaluza-Klein and winding modes. So I include a set of massive string modes, but I don't include the full spectrum of string theory. And there, of course, the immediate issue arises, is that a consistent thing to do? Should I expect this theory to exist? And there was a very nice result roughly 2 years ago by Ashok Sen, who proved by a general argument that starting from closed string field theory, there's a procedure to integrate out the massive string modes that we don't want to describe in this setup. So that theory really should exist, and in particular, it should be governed by a suitable L-infinity algebra. So that's now the problem. Defining the L-infinity algebra that does the job, and I just indicated here one little bracket. So if you do the Courant story, sort of this bracket is equal to 0, where chi1 and chi2 belong to the space. Because in the Courant story, we cut the L-infinity algebra at this stage. There are no further spaces here. And this is consistent because here I have the strong constraint, because this guy is equal to 0. But if it's no longer equal to 0, that means you have to switch on more stuff, and the challenge then is to do it in a consistent manner. And that's still extremely non-trivial, because string theory tells you that you have to introduce certain non-local projected products, and that they get sort of nested then in the computations of gauge covariance and etc. And we don't know how to do it so far, but at least there's an abstract argument that it should exist. And also we know which algebraic structure should be behind it. All right, any questions about this?
So, I'm very naive. So on the slide you've written dm chi2 equals 0. And on the board you wrote something which is linear in the field. So what?
Yeah, so what I meant to say is, so what we usually do in double field theory, and that's what I mean by this equation, if we have an expression like this, where you get this mixed term if you work it out, we simply set it by hand equal to 0. And that's what I mean by this expression over there. That's what we usually do. But in the full string theory, we shouldn't really do this. We should allow for this, for the naive product, for this to be non-zero, or equivalent. You should have to introduce a new type of product, which is non-local and makes it 0 automatically, so that you don't have to impose it by hand. And that's just the challenge, the problem that one should solve at some point, but it's not been solved yet.
When you say non-local, what kind of non-locality do you mean?
So what you usually do is, or what is suggested by string field theory, is
That was the definition.
so what is suggested by string field theory is, on the torus, for instance, that we take two functions that satisfy the constraint, you Fourier expand them, and you multiply them, you simply set to 0 all the Fourier modes that violate the constraint. So you chop out the Fourier modes that you don't like, and that's of course an extremely non-local operation. And the resulting product is very nasty. It's not, doesn't have any nice properties. And then the challenge would be to encode the failure of this product to satisfy nice relations like associativity, etc., to encode this in terms of infinity structures of this type. More questions?
Before you go, can you just briefly say again what chi, xi are, and what are the names for these? You said
So chi is the you can think of as trivial gauge parameters. That means if you act with L1, you get a gauge parameter that doesn't act on fields. So it's also gauge symmetry for gauge symmetries. Psi is a gauge parameter. So acting via L1, it acts on psi, which are the fields, psi are the fundamental fields, and x1 is two other field equations.
So here, your equation of motion is that the fields belong to the zero locus of the homological vector field, basically, right? The second, the line 0 equals L1 of psi. So that means that in the zero locus of the homological vector field corresponding to this L1-algebra.
I think that's the right language, yeah.
On the trick, you need to put to 0 fields with non-zero degree.
Here is algebra in antisymmetric version, so with a shift of grading. So to get homological vector field, you need to shift grading by 1, and you then get the right degrees.
Yeah, I think that's true.
It's antisymmetric, and you need to make it symmetric.
Right, exactly, yeah, that's right. So I should say for the non-experts, so there's a particular set of conventions, but it's not the only possible one. In fact, the string field theory is more naturally formulated in terms of that conventions where the brackets become graded symmetric rather than graded antisymmetric. And in this case, you can interpret these relations sometimes more naturally as a certain operator squared into 0, which is, I think, what you refer to as a homological vector field. All right. Okay. Let me now come to this second aspect, the Lightness algebras, or Lightness-Lode-algebras conditional assignments theory. So here's the definition: a Lightness or Lode algebra is just a vector space equipped with a bilinear product. And this product should satisfy this relation. So this looks, that's why it's called Lightness algebra, because you can think of this X acting on this product by a Lightness rule. And the important point here is that this product does not need to satisfy any symmetry or anti-symmetry properties. So gel has a symmetric and anti-symmetric part. And if the product happens to be anti-symmetric, then this reduces to Lie algebra. So you can check that these are the relations to the Jacobi identities for Lie algebra, but if it has a symmetric part, it's more general. Now this is interesting because this is actually sufficient in order to define consistent symmetry variations. So normally we like to think in terms of Lie algebras because then you have a natural adjoint action and we can talk about representations. But actually for consistency this is sufficient in the following sense. So you immediately have symmetry variations on the vector space itself, which is defined by this product. So the variation here, delta xy, for which I introduced you also different notation, which should remind you of the Lie derivative, because that's how we usually write it, like David's talk in double and exceptional field theory. And that's simply defined by this product. And now you can check that these operators close. So if I work out the commutator, I get this combination over here, and then using the Leibniz relation, I can rewrite it like this, and so finally in terms of this operator itself. So this is all I need in order to establish closure. So the commutator of two such operators gives another such operator. And so that means these are good transformations in the field theory. Now I can derive now two immediate consequences. If I antisymmetrize this equation, because the left-hand side is manifestly antisymmetric, I can antisymmetrize, I get the same on the left-hand side. On the right-hand side here, I get the antisymmetric part of this guy. And if I symmetrize, I get 0 on the left-hand side, and so that I learn that the L with respect to the symmetric part acts trivially. Okay? So that means I can already tell that they are trivial transformations, which are just given by the symmetric part. I can also work out now the Jacobiator. So for the antisymmetric part, I cannot think of this as defining a Lie algebra, because if I work out the Jacobiator, so it means the combination that would be 0 for Lie algebra, I don't get 0, but I rather get this symmetric combination. So I get something that's not 0, but it's trivially according to this criterion, that the corresponding symmetry transformation is trivial on fields. And moreover, I can check that this trivial space forms an ideal of the bracket, the antisymmetric bracket, in the sense that if I take the bracket of anything with a symmetric part, it can also be rewritten as a symmetric part. And it turns out that this is actually sufficient in order to prove that any lightness algebra then defines an L-infinity algebra where the L2 is given by the bracket, and I have to define suitable higher brackets, of course. So in that sense, that's a very easy way to construct L-infinity algebras. So that's just the abstract definition, and now I can introduce a gauge theory for Lightness algebras, and more specifically I can define a Schoen-Simons action in 3D. So potentially I can go to higher dimensions, but did you have a question? Or you
Yes, yes. Okay, so my question is, what about classification of these algebras? How is that?
Well, I don't know anything about classifications. I'm not sure of the methods. I will give you examples.
Simply Q manifolds have associated Lightness algebra. That would be.
An example is given by the general construction of binary derived bracket, which is due to Eletros-Monchar-Swap. So you have Lie superalgebra and have an element that squares to 0. Well, then you define a new bracket, which is not necessarily anti-symmetric or symmetric. It's Lodé algebra.
All right. Okay, let me define the gauge theory. So, like in standard Yang-Mills theory, where we start from a Lie algebra, now let's start from the Leibniz algebra and consider one forms taking values in this Leibniz algebra. And then I can write the natural version of the Yang-Mills gauge transformation, which looks like this. So this is like the standard covariant derivative, except that I used here this Leibniz product. And then I can check that these gauge transformations close, but actually they only close up to certain higher gauge transformations, and that corresponds to the fact that in general I have trivial parameters, as we discussed in the previous slide. So by themselves these are not actually consistent, but I can, leaving out all the details, but you can sort of make it consistent by introducing higher order gauge transformations, which correspond to introducing a B field or a 2-form with its associated gauge symmetry. But at this level we don't actually need it, because I can write down the generalized Schoen-Simons action just in the standard fashion. So that is sort of the formula here is exactly what you would write down for Schoen-Simons theory, except that now you use this Leibniz Lodé structure. And remember, although this is anti-symmetrized, so I could also write it as a bracket, but this bracket is not a Lie algebra. So in that sense, it's more general. But it's still consistent because at the same time I imposed the condition that this inner product here is actually not degenerate, but has this property that if I take any vector, pair any vector with a trivial part given by the symmetrized combination, I demand it to be 0. And it turns out that that's actually realized in all the examples that are of interest. In fact, it's the situation in 3-dimensional gauge supergravity in the embedding tensor formalism as developed by Henning and Nicolai, already 16, 17 years ago. So the statement is that any Leibniz algebra with an inner product having the right invariance properties defines a consistent Schoen-Simons theory. Now, in general dimensions, I expect there will be a more general story where you have to introduce a full-fledged tensor hierarchy. So by tensor hierarchy, I mean this what a hierarchy I just alluded to, where you have not just the 1-form, but also 2-form, 3-form, and potentially can go higher and higher. In 3 dimensions, you don't see any of that. It's sufficient for writing an action to consider the 1-forms, but in general you see this hierarchy, and that will sort of make manifest more and more of the structure of the corresponding L-infinity algebra. All right, so now let me discuss a particular class of examples, and that is the construction which goes back to the gauge supergravity construction, and which realizes Leibniz algebras starting from the general Lie algebras, but acting sort of on the dual space via the coadjoint action. So that's, I think, sort of an unusual construction, and so I hope I can explain this here. So the starting point here is that we have this embedding tensor formalism in 3D, by which we mean that we start from the general Lie algebra. So this I denote by G here, and that's the structure constant sitting here. So the indices Mn are adjoint indices. And now we define the structure constants of the gauge algebra, not as these structure constants, but as these objects here, x, m, and k, with theta here is what we call the embedding tensor. So we take the original structure constant and construct it with the embedding tensor this way. And the embedding tensor is a symmetric tensor, it's this index structure, and it defines in particular the covariant derivative of the theory. So if you have a gauging, you start with a global symmetry of the ungauged theory, which is this Lie algebra here, and then we define the covariant derivative in this fashion using the embedding tensor. Okay, and now the statement is that this structure here, x, m, and k, defines the Lightness low-day algebra. So we'll write this in the basis on indices, it looks like this. And what we, in the embedding tensor formula, call the quadratic constraint is nothing but the statement that this product defines the Lightness algebra. Okay, so that is just a consistency condition that the transformations following from the structure do close. Okay? So that's just this sort of the standard discussion in gauge supergravity. And now I would like to formulate this in a more invariant language, not just to please the mathematicians here, but also to generalize that to infinite dimensional structures. So then I will come sort of back to the discussion of exceptional and double field theory, because in that case, the structure that I will discuss is the structure of generalized diffeomorphisms on some generalized internal space. So that's something infinite dimensional, and it turns out that these internal generalized diffeomorphisms do define a Lightness algebra, not a Lie algebra. In order to relate this to the embedding tensor formalism, I have now to sort of reformulate this in an invariant language. So that works as follows. So we got now passed from the space of the original Lie algebra to the dual space G star. So A here is a dual, is a covector. That means an x on a vector is the standard construction here. So that's the infinite, the finite dimensional formula. And then I have a notion of the coadjoint action of the Lie algebra on the dual space, and that's defined as follows. So the coadjoint action with respect to a vector zeta on a covector A is defined by this formula. So this coadjoint action gives me another covector, which naturally acts on the vector to give a number, and that number is defined by this combination here. So I take the original Lie bracket between zeta and b, and then I act as the covector in order to get a number. And if I write this out in terms of the basis, the action is given here. So now I can check that the invariant way of thinking of the embedding tensor is as a map, not from the Lie algebra, but from the dual of the Lie algebra, G star tensor G star into R. And the formula here that I used to define the Lightness structure, the structure constant x in terms of theta and f, can now be translated to this expression here, that the Lightness product is defined implicitly by its action on B by this formula here. So the Lightness Laudet structure is not defined on the space of the original Lie algebra, but on the dual space. So that's sort of a crucial step here.
It looks like a dual to derived bracket construction.
Say again?
It looks like dual to derived bracket construction, because in derived bracket you start from operator on your original Lie algebra, and you derive new bracket,
Right.
define new bracket on the Lie algebra. And here you have operator which acts from the algebra to the dual space.
Yes.
And then use coadjoint instead of adjoint.
Yes. Yes.
Is there any direct comparison? So
I don't know. We should discuss that. But yeah, no, but you summarized it correctly, I think. So this can be made also a little more intuitive, perhaps, if you rethink this embedding tensor as a map from G star to G. So in indices, you would write something like this. So here, you noted that now I borrowed theta in order to distinguish it. So you act here on the dual basis. T tilde is a dual basis. And you use the embedding tensor to rewrite it in terms of the original basis of G. So that gives you a natural map. Or in invariant terms, you can say that the capital theta at before is related to the bar theta with this combination here. So bar theta of B gives you a vector, so you can act as a covector to give a number. And then you can prove, it's not immediately obvious perhaps in the formulas I've given you, but you can prove that the Lightness algebra is now defined by this coadjoint action with respect on sort of A times B is the co-adjoint action of B with respect to var theta of A. So you take the A, you map it to G, and then you have a natural co-adjoint action. And more generally, any G representation, any representation R of the original Lie algebra now becomes a representation of this Leibniz algebra, where you just use this map for theta. And as I said, the invariance, yeah, so now you can actually prove, which is nice, that if theta is invariant under this Leibniz action, which we think of as a quadratic constraint, then this implies that we have a Leibniz algebra. So that actually, Leibniz algebra is a difficult relation, it's a cubic relation. This is a little simpler, so it's nice to have this.
That's statement only?
No, it actually, in the finite dimension case, it goes in both directions. In the infinite dimension case, it doesn't. All right, so let me give you now an example, which brings us back to the exceptional field theory language. And the exceptional group I'm considering now is E8. So for E8, we have a notion of generalized Lie derivatives, Steger was reviewing. And this notion, these generalized Lie derivatives can now actually be nicely recovered from an embedding tensor using this more abstract viewpoint. So the starting point here is a global Lie algebra, which we can think of as sort of as a kind of the symmetry of the decompactification limit of exceptional field theory, where you think of the internal space as a large torus in the simplest case, and you send the radii of all circles to infinity. In this case, you get an enhanced global internal symmetry, which consists of internal diffeomorphisms, with parameter lambda m, and sort of global but y-dependent E8 rotations, with parameter sigma m, so E8. So m are now adjoint indices or fundamental indices of E8. And you can work out the Lie bracket of two such guys, and it's given here. So the first component is just the standard Lie bracket of vector fields, and then you have an extra component using also the structure constants of E8. Okay, so that's the starting point of the Lie algebra. Now we have to discuss the dual space. And for the dual space, we introduce these covectors, calligraphic A here, which also now have two components. And you think of this as a covector because there's a natural pair between a covector and a vector, which is given by this integral. So you pair A with Q and B with P, and this you declare to be the invariant pairing between vector and covector. And now you can work out what the co-adjoint action is by simply checking the variance of this combination. So that gives you the formula for the co-adjoint action on the covector here, which I hadn't written. But that's now defined. And now the question is, what is the embedding tensor? So if I give you an embedding tensor and I know what the co-adjoint action is, I'm done. And the statement is the embedding tensor is this combination here. So that's actually a very natural expression. You take two covectors, because remember the embedding tensor is defined on the dual space. You take two covectors of this form, and then you have a natural pairing between these two components, AM, BM. But you have to add one more term, which you can define, which is nice, given here. And it turns out that with this choice of the embedding tensor, everything works out. So in particular, you do define the Lightness algebra. So in case supergravity language, it means the quadratic constraint is satisfied. And in particular, you can define our Schoen-Simons theory based on this structure here. So you can define all kinds of things. You can define this map for theta from this relation to define the generalized Lie derivatives. And the generalized Lie derivatives of E8, which the way we originally found them looked extremely strange and somewhat convoluted, now come out very naturally from this construction. And in particular, based on this bilinear form, you can now define the Schoen-Simons action, just plugging into this general formula here. And that reproduces exactly the Schoen-Simons action of E8 exceptional field theory. Yeah.
Very trivial question. You've got indices up and indices down for your the second line there at the top for your E8.
Yes.
Is there
Well, it's a little fake in the sense that E8 has a Cartan-Killing form, so I can always raise and lower. So the position of the indices actually here, this level doesn't mean too much. We just sort of write it in this way because it's sort of natural to think of B as a dual of A, because you always have this pairing between upper and lower. But in principle, there's a metric between these two.
Okay, that's what we
Okay, almost done.
So sorry, just go back again. So
Yeah.
an F is the structure constant
Of E8.
of EA.
Yes.
And then so it's this.
Right.
So you do the bracket is the usual lecternized Lie, which is with the lambda, and then you've got this additional E8 in 6.
Well, so this is not the usual bracket we have the exceptional feature. This is actually generally Lie bracket, which is an auxiliary object that we use to define on the dual space the actual bracket or Lightness structure which that we do see arise.
Because that seems to have double E8s.
Yeah, exactly. So, and that is very nice because, as you recall, in E8 exceptional field theory, you have this doubling of gauge parameters. And so you have not just a naive one, but you use a second set of parameters. And here this naturally comes out from the fact that the global Lie algorithm we consider is not just E8, or it's not just diffeomorphisms on this 248-dimensional space, but it's rather sort of the semi-direct product between the two. But this is just an auxiliary Lie algebra, which you can use as a starting point to derive the Leibniz algebra on the dual space that is actually the structure of exceptional field theory. All right, so let me summarize. So the algebraic structures beyond Lie algebras arise very naturally in string and N theory, as you see here. In particular, the tensor hierarchy of gauge that we see in gauge supergravity and exceptional field theory really is most naturally formulated in terms of these infinity type structures or L-infinity algebras, and kind of difficult or natural in terms of Lie algebras. They also, as I said, natural Schoen-Simons theories beyond Lie algebras. As I try to review in particular, something I couldn't explain is that there's a formulation of the complete topological sector of this E8 exceptional field theory in exactly that language that not only has the internal gauge vectors, but also the external Dreibein and spin connections, the part of 3D gravity, and combines it all into a larger algebraic structure. So that's a very nice generalization of these classic results due to Cooper and Townsend and Whitten, that pure 3D gravity can be interpreted as a Schoen-Simons gauge theory. But now it's not a suitable Lie algebra, it's a Leibniz-Lode algebra that does the job. And that includes, so that captures the topological subsector of 11-dimensional supergravity. Now we can also try to describe globally supersymmetric 3D theories in this language, for instance, 3D superconformal field theories, which now you can ask, can I include infinite dimensional gauge groups? That's work in progress. And then, of course, the big picture in this endeavor is this sort of the large unifying algebraic structure of M theory. I mean, we will hear later from Henning about the affine E9, so it's already an infinite dimensional group, which works analogously to the E8. And so the question is, what would be the large, so is there a large algebraic structure that encompasses everything at the same time? And I think it's natural to conjecture that Lie algebra is maybe too rigid, or maybe sort of a slightly wrong framework in order to do this, and we really have to switch on these non-trivial structures. All right, thank you very much.
Any questions? So in the 80s, there used to be a lot of constructions for exceptional group covariant formulations of elemental supergravity, right? Dirichlet-Nicolai.
Yeah, that's a Dirichlet-Nicolai was sort of the natural starting point.
Yeah, my question is, that seemed complicated. Is this a way to organize and simplify, perhaps, geometrically?
Well, it was complicated for them because they didn't really understand the underlying structures, what you have to do to really write it in a covariant way. And I think that's the crucial ingredient is really to introduce these extra coordinates, so that you have a covariance principle, namely these groups DDD, and then you can try to write everything in a covariant language. And then there's not so much you can do. I mean, it's still complicated, of course, but it's not hopeless anymore. I think that's the part they were missing. Sort of in their case, really just to implement ED7. So that's what they could not do to implement ED7.
But I mean, conceptually, does this go towards answering or simplifying or completing that kind of direction?
Yeah, I would say this is completing that research program started by the Olaf.
Sorry, John.
Can you say a few more words about the evidence that lead theory is slightly wrong? The basic.
Well, it's difficult to make a sort of very sharp statement along those lines, because morally, Lie-algebras are always sufficient, because you can always say, well, the extra stuff you have, you can sort of mod out, and you're not working on the right space. So effectively, if you have L1-algebras, it sort of means that you're working on a too large space. You should work on a smaller space, and then you could get away with it. But that's true, but by doing so, you would lose some of the manifest properties like duality covariance you would like to see. So it's sort of a bit like a philosophical, aesthetic attitude that you follow in order to, you want to make as much manifest as possible. And if that's true, then you're forced to introduce these higher algebraic structures.
Yeah, this infinity algebra approach you proposed looks to be quite similar to what Kevin Costello and his people are doing, which comes from Lewis' theory of formal modular problems. So is this, did you check what it will relate, try to relate this stuff with Costello?
I downloaded his book on my laptop.
That's
the first thing I downloaded.
Because I think Costello
Legally, hopefully.
really picking up this formal modular perspective and then manipulating these things.
Yeah, I know many people tell me that seems to be kind of profound, but I haven't really managed to study it.
Are these transimus theories topological?
Yes.
And are there any instances where you can have some control over representation theory so that you could hope to have a combinatorial quantization like for compact Lie algebras, complex simple Lie algebras?
I haven't really thought about this. I don't know. I mean, one question is already to give a sort of a global definition of this action I wrote down. Like in standard transimus theory, you think of this coming from four dimensions as F wedge F. And if you do this, of course, a slightly different question, but I guess if you want to do that, you have to introduce more of these higher forms and do this the tensor hierarchy construction. Yeah, I could have a repush that further.
If I may, I would just like to make a remark concerning the recurring question of if there's two examples or maybe a justification of energy algebras. So one thing good to know is that every DG Lie algebra is an example of an infinity algebra that happens to have only the binary and binary bracket.
Yeah, or any Lie algebra is another infinity algebra.
Any what?
Any Lie algebra is also.
Well, but the thing is, the DG Lie algebra is actually equivalent to an infinity algebra. Homogeneity theory of DG algebras is equivalent to that of an infinity algebras. And on that DG algebra side has been shown way back in the 69 by Quillen that every an infinity algebra in positive degree is equivalent to a rational space. So rational homotopy theory is the same as an infinity algebra theory in positive degree. So there's a huge supply of examples, but also at the same time it shows there's not a hope to have a classification of all of it because it's very rich, but of course you can start classifying on certain assumptions. You know, I'm just trying to emphasize L-infinity stuff was way back. There's a huge supply. I mean, there's no lack of examples.
Right, but the point you're making is also that there's a notion of equivalence that tells you you don't really need it. That's going back to the points we were just discussing. Say if all of them are equivalent to DG algebras,
DG
then,
algebras, yeah.
then in principle, it should always be enough to work with that, right? So that's sort of the balance of what you actually want.
To equivalence, but sometimes it's one side is more convenient than the
Right,
other.
exactly.
It's only the infinitesimal case, of course. If you want to find global structures, you need it. Because you want to integrate groups and things.
I see, I see.
And you get string of 5 steps.
In your Chern-Simons theory based on this, like, it's still cubic in the
Right.
physics,
Yes.
right?
Yes.
And can you show that it is not equivalent to Chern-Simons based on genuine Lie algebra? So it's a non-trivial.
Well, I think, no, actually, you can.
Because you see,
you
inside
can
there is still
abstractly
the standard.
No, no, I think actually you can abstractly prove that it is equivalent to a normal Chern-Simons theory with a Lie algebra, except that that Lie algebra is not a natural object anymore. It's defined on a space that we don't like because we can't write explicit formulas. But morally, so in fact, what you can always say, I think, or always do, is that exactly. So if I look at this Lightness algebra story, I can just pass to a quotient space where I mod out these trivial symmetric parts, and then I have a generating Lie algebra. And also here, this inner product becomes non-degenerate. And that on that space, I think it should be standard Chern-Simons theory. It's just that on that space, it's not convenient to work because the gauge structure cannot be written in any explicit formulas. It's sort of like saying a standard gauge theory, and Mills theory, whatever. I don't like gauge redundancy, so I pass over to the space of gauge invariant objects. Then there's no gauge symmetry anymore. And it's philosophically, that's true, but you can't do computations with that attitude.
Another reason why you wouldn't do what you say is go to a gauge invariant formulation is that you still have information from Wilson lines. So
Right,
actually
right.
having the gauge symmetry is more.
Right.
There are physical parts of the gauge symmetry, local, not local operators.
Right, right. I mean, yeah.
Okay, let's see further questions. Sorry, one more question. Okay.
Just one. What is the situation with parity? Is it just broken in this Chern-Simons action? Or is it that?
I guess that depends on the example. You mentioned that there are examples you can write where, I mean, generically it's broken. If you have a Chern-Simons theory, but I think the special examples where you can arrange non-trivial parity transformations that fix it.
Sorry, very quickly, you've got a typo on your slide, so it's just on the second term of the Chern-Simons. Oh no, maybe not. No, it's my reading. I'm sorry.
Where do you think it was the time?
No, I missed it. No.